Okay, so here is the first day that we're like actually defining what a rational function is. All it is the ratio of two polynomial functions such that neither of them are 0, because you can't divide by 0 over here, and they do not have any common factors. So what does a common factor mean? You can't have x plus 3 over x plus 3 and call that a rational function, because they'll just cancel each other out, right? And then you just have a constant function of 1. So on the exploration that you did, one of you got a straight line for one of them. Not everyone finished, I don't think either. Like, did you finish page 201, the back page yet? We did finish them all in here? Okay, one of those should have come out as a straight line. The reason it came out as a straight line is because something canceled. All right, so here's the parent function when it's just 1 over x. It says, well, without graphing it, how could you determine its domain? Where will the denominator be 0? So where will the denominator be 0? Where did you say? No, at 0. So when x equals 0. So the domain is going to be x cannot be 0, right? So our domain is going to be x will never be 0, because you can't have 0 in the denominator. All right, so then how can we graph a function that we've never seen before? We could use the strategy of a table of values. Everyone sees this is page 203, right? So if I plug in -2, what would I get in that fraction? 1 over -2, right? So that's the number -1/2. So let's plot -2, comma, -1/2 on our graph. What if I plug in -1? What is 1 divided by -1? Right, this is the function we're plugging the numbers into. 1 divided by -1 is -1, right? So -1, -1 would be here. All right, what if I take 1 and divide by -1/2? Have you ever heard the expression, when dividing by a fraction, don't be shy, flip the second and multiply? So dividing by a fraction is the same as multiplying by the reciprocal of the fraction. So if you have $1 and you divide it by 50-cent pieces, how many 50-cent pieces would you have? 2 50-cent pieces. So if I take 1 and I divide by -1/2, I actually have -2. So when I'm at -1/2, I'm down here at -2. What if I divide it into quarters? What would be 1 divided by basically 4 quarters? You'd have 4 of them, right? So 1 divided by -1/4, you're multiplying by the reciprocal, -4 over 1, and your answer is -4. So as I get closer and closer in this direction, now I'm at 1, 2, 3, 4 down here. What this looks like is this curved elbow, and it basically gets closer and closer to 0, and it gets closer and closer to this y-axis, but it doesn't actually touch either of the axes. So it just gets closer and closer, closer and closer. What happens at 0? We already said the domain can never be 0, right? I can never plug in 0 into the denominator. So you're going to draw a vertical dotted line. It's kind of hard to see this, but it's just supposed to be a vertical dotted line, which is an asymptote. That means my graph will never touch x equals 0, because that is an asymptote. So we talked about vertical asymptotes a little bit on that exploration. All right, so now I'm going to write error or undefined. What happens now if I take 1 and I divide by 1/4? So 0.25 is the same as 1/4. And if you don't know, we could also check on this calculator. 1 divided by 1/4 is 4. So 0.25, now I'm at 1, 2, 3, 4, I'm up here. And what about at 1/2? What's 1 divided by 1/2? 2. So at 1/2, I'm at 2. And what about 1? Well, 1 divided by 1 is just 1. So I'm at 1, 1 over here. And what about 2? Well, 1 divided by 2 is 1/2, so I'd be right here. So this is another elbow that gets really close to the y-axis and then really close to the x-axis. Because what if I plugged in like 10? I would have 1/10. So all the way over here, I'm at 1/10. I'm getting closer and closer. All right, so that's the parent function. It basically goes through these key points, 1, 1, -1, -1, and it's just 2 elbows going in either direction. So that's the parent function of a rational function graph. And it says determine the end behavior. End behavior means as I go to the right, what's happening? What is that arrow getting really close to? 0. As I go this direction, I'm also getting really close to 0, right? So I could say as x goes to infinity, y goes closer to 0. So, you know, like before we were saying the right end goes up. Right now the right end is approaching 0. And if I write x goes to negative infinity, y is also approaching 0. What is the range then of this function? So we said the domain is x can never equal 0. Well, the range is the same thing. Y will never equal 0 either. So our range is y can never be 0. So it says rational functions are a type of function that has asymptotes. An asymptote is a line that the curve approaches as it heads towards infinity. And what asymptotes do you see in the graph? So basically our two asymptotes are x equals 0 and y equals 0. So x equals 0 and y equals 0 are the two asymptotes of the parent function. So these things are going to get shifted all around, and you're going to have to find the new asymptotes. So think about your transformation rules. So before we look at the functions on the next page, if I just took a function and I did x squared plus 2, what is that transformation from our unit 1 test? What is it? Up to. Or yeah, up to. What if I took x minus 3 and squared it? What direction did I just move it? To the right by 3. So I can replace x squared with any function I want. So my function right now is 1 over x. If I add 2, it's going to shift everything up. If I have 1 over x minus 3, now see how that x minus 3 is in the bottom? It's going to shift everything to the right. So on this page, we are trying to identify the transformation rules. So what two things have happened to this function? Up to, and what else? Right one. So my key points for the parent function were at 1, 1 and -1, -1. So I'm going to move those points. This is the parent function. And I also have to move my asymptotes. So my asymptotes are normally at 0 for x and 0 for y. 1, 1 and -1, -1. So this is 1, 1. This is -1, -1. So on this graph, I'm going to take that parent function and shift it right 1 and up 2. And if you want to, you could actually just dot in the parent function. Like here are my 2 dots for my elbows. So I could just go right 1 and up 2. Here would be my new point. And I could go right 1 and up 2. Here's my other point. So those little X's are my new transformed points. What is this? The horizontal line is going to go up 2. Right? So if I go up 2, now my asymptote is here. And if I go right 1, my new asymptote would be here. So I've moved where that little yellow cross went because my asymptotes have moved right 1 and up 2. And then my elbows kind of go through those points with that shift. And this is hard. We're usually not going to graph rational functions this way. We're going to use a different set of skills, but If it was an easy one like this on the SAT, it'd be nice to be able to just read your transformation rules from the original function and not have to do it the way I'm going to teach you kind of the end of this week. It says give the vertical asymptotes and the domain and the range. So this is x equals 1 and this is y equals 2. Those are my asymptotes, right? Because those are just vertical lines. But if I have to write the domain and the range, I'm going to write those differently. I'm going to write x can never equal 1, and I'm going to write y can never equal 2. So whatever the asymptote is, that's what you're excluding from your range. And whatever your vertical asymptote is, that's what you're excluding from your domain. So a lot of new on this parent function. See if you can do B and C. If you want to use a pencil, if you want to use a partner, if you want to look at your notes, that's fine. But you can actually check your answer on the graphing calculator. So like in your head, or graph it with a pencil first, and then you could check it on the graphing calculator to make sure that you're getting it in the correct direction. And I'll kind of put them up at the, okay, so when I went, this is left 3, this is down 1, so I moved my cross of my asymptotes, left 3, down 1, there's the center of the cross. So those two parts of your elbow kind of go diagonally away from the center. And then you draw a curve. And then your asymptote, if this is a horizontal line at -1, y equals -1 is the asymptote. Y can never equal -1 is the range. So whatever your vertical asymptote is, that becomes what your domain can't be. Oh, I just gave her my pen. Let's see. This negative sign, this +1, and this -3. So this is a flip over the x-axis upside down. This is left 1, and this is down 3. Right? So you've got those 3 things to do. So when you graph your parent function, instead of thinking of those elbows in that direction, if you're flipping it, your elbows are now going to go in that direction because they're flipped over. So I'd go left 1, down 1, 2, 3 here. That's the center of my asymptote. Whoops, that's not my point. Right? I'm going to go here for a dot and here for a dot, and those will be my elbows. And then how would I write my equations? This would be at y equals -3. And then this one would be at x equals -1. Those are my asymptotes. But to write my domain and my range, I put a cross through. So x will never be -1 because that's an asymptote. Y will never be -3 because that's an asymptote. And we're going to start learning more about these functions. Okay, they all have asymptotes. They all have a curve in kind of opposite, or they might be next to each other. They all have x or y intercepts. I didn't have you look for x intercepts this time, but that's kind of the general idea of the parent function anyway.